Hey, what's up, everybody? Back again. Still adding and subtracting functions. No change there. But what has changed is this time out, we're going to add a little extra to these questions. We're going to find the domain of our new function, our new addition or subtraction function. So before we do that, okay, we're just going to review some things here. First of all, if you have a degree 1 or a degree 2 function, which is linear that you learned in grade 10, or parabolas, which you've learned in grade 11, the domains for those are all real numbers. Or if you express it using the new interval notation, it would be negative infinity to positive infinity. Okay, so those are always going to be your domains for any linear or quadratic function. Some other types of functions that show up in these questions, however, are radical functions, and you've already studied those in 12A with Ms. Johnson, but let's do a little review of this, okay? How do we get the domain of y is equal to the square root of x plus 6? So first of all, this isn't an addition or subtraction function. This is just some review right here. How do you get the domain for the square root of x plus 6? Well, what you can do is, first of all, let's remind ourselves that this is a translation of the basic y is equal to the square root of x function, which begins at 0, 0, and then goes up and to the right. So you can see that the domain for this is starting at 0, going to infinity, with a square bracket on the 0 because it actually touches that point. Okay, there's no vertical asymptote at 0 or anything like that. So it actually includes 0, but whenever we use infinity, we'll always use a round bracket because there's no specific infinity point. It just goes on forever. So we have the square root of x. So if we do the square root of x plus 6, well, if we think about it in terms of a mapping notation, then that would be x minus 6 in the mapping notation, which means that the graph would move 6 units to the left. So we would wind up here at negative 6 and nothing else happening. So you can see that the domain for this would be from negative 6 to infinity. No reflections or anything. It just happened to move 6 units to the left. So this would be the new domain. So we're going to keep all of this in mind when getting domains of subtraction or addition functions. And in this case here, we have two functions, f and g. G is a linear function, and f is a square root function like we just looked at. So the first question doesn't even ask about domain. It's just asking you to calculate h of x like we did before, and f of x is square root of x minus 1. G of x is x minus 2, and we're going to subtract them. The reason for me putting these in brackets is because when I subtract a binomial, this subtraction sign has to go to both terms, but there's not much simplification that we can do here. Okay, the square root function, we can't really add or subtract to anything, so this is as best as I can do. Okay, this is the equation of h of x. You cannot add square roots to just regular x's or to numbers, so that's as simplified as we can get. State the domain of h of x. This is what's new. So in order to get the domain of your composite function, you have to first of all look at the domains for f and g separately. Now, if you look at g, that is a linear function, so we can say that the domain is all real numbers from negative infinity to positive infinity. And f has a restricted domain, which you could, based on the previous example, you could say that this goes from positive 1 to infinity. Or if you need to do a rough sketch like we did in the review example, then go right ahead. In the mapping notation, it would be x plus 1. So we would end up with something like this. It would shift 1 unit to the right, and you can see that that is the domain. Okay, 1 to infinity, including the value of 1. So what is the domain of our composite function, or sorry, our addition or subtraction function? Well, what you do is you basically get the domain of each individual piece, and then your domain overall is the domain that both places have in common. So what you can do here is you can say, all right, this is just one method you could use. You could say, okay, well, in this one, in f, using a number line as an example, we have the domain is everything to the right of 1. Whereas in g, the domain for this, it's all real numbers, so it's everything is included. So for H, you want for the subtraction or addition function done the same way, you want to get the domain. It's a domain that is in common in both, and that would be from 1 to infinity. Okay, now you don't have to draw those number lines. That's just one suggestion on how to get the restricted common domain. And if you take a look at on Desmos, I've graphed everything. And you can see right here that I've graphed each individual function. And then in green, you have the addition function, which actually is a mistake because it was a subtraction function. So sorry about that. I've made a mistake here, but we're just going to go ahead. Okay, the subtraction function is what it really should be, and that would give us a different result. But one thing you know is that the domain is from 1 to infinity. Okay, so it keeps going forever and ever, all right, to the right. To the left, it does not, okay, and that is based off of this domain right here, which is what's common in terms of the original functions, the basic f and g functions. What is the domain of each of those? What domain do they have in common?